Today I'm here presenting Streaming with Structure. My name's Kate Stanley. I'm a software developer at IBM, and I work on a product called IBM Event Streams. And as Bruno said, today I'm going to be talking to you about streaming with structure. So first, I'm going to start with a coffee example because everyone loves a good coffee example. So when building applications, people often start building them and breaking them down into microservices that have HTTP communication between them. So we have an example here, and you can go see the code on GitHub, but this has some coffee lovers making requests to a coffee shop, then forwards on to a barista. And if you run this example, it works fine with just a few coffee lovers, but people soon start asking, well, how can I make this system more resilient? How can I stop having bottlenecks? What can I do to perhaps introduce some decoupling between the coffee shop and the barista so the barista isn't getting overwhelmed with orders? And we can do this by looking at event-driven architecture. So event-driven architecture is this idea of having your publishing microservices putting all of their events onto an event backbone. Then you have subscribing microservices that pull off those events, process them, and perhaps put new events onto the backbone. So if we add this into our coffee shop demo, we can now see that we have a barista who is looking at the event backbone for all of the orders. So what this means is the barista is free to pick up the orders as and when it's ready to deal with them. And then once the orders have been completed, add them onto a queue that can then be forwarded across to the board so the coffee lovers know that their coffee is ready. So moving to this sort of system allows us to have this decoupling between the coffee shop and the barista. The barista can go have a break, come back and process anything that's arrived while they've been away. And often we want to, in the current situation, people are looking at Kafka. So for those of you who aren't aware, Kafka is an open source distributed streaming platform. It has exploded in popularity in the last few years because it's ideal for a lot of different use cases. It's really, really configurable, and it has such a great community around it that is building on it every single day. These are some of the core features that Kafka provides. It gives you stream history, so that means that you can replay events and have multiple consumers consuming from different points in the stream. It works with immutable data, and it's highly available, scalable, and provides scalable consumption. It's a publish-subscribe model, so it fits perfectly with this idea of looking at decoupling your microservices. But often people add Kafka into their systems and assume that that's enough to provide all the decoupling that they want. But actually, that's not necessarily the case. So that's what I'm going to talk about today, and how you can make use of things like Kafka, but do it in a fully decoupled way. So first of all, something to know about Kafka is that the data in Kafka is stored in bytes. All of the data inside the Kafka breakers is in bytes, no matter who has sent it in. So what this means is that producers and consumers of Kafka events, they have to actually do some processing of the data before it gets sent into Kafka so that it's in this byte format. And they can do this in the sort of way you would guess, which is using serializers and deserializers. So Kafka provides some libraries that you can use to serialize data and put it into Kafka and then deserialize it at the other end. Okay, so we know that we've got bytes coming through Kafka and we're producing and consuming. But what's the actual problem with running with this Kafka system, and where will you find that is still coupling? Well, that's if you look at, for example, a string serializer. So say in my coffee shop, all of my events, I've decided I'm going to send them through with an ID, product name, the customer, and then the size of the order. So for now, we'll go with 1, 2, 3, 4, hot chocolate, Kate, and small. So I actually don't like to drink coffee, so that's why I always use hot chocolate in my examples. So if I send this through, as long as the barista understands that this is the format of all the messages that should arrive, the barista can make the coffee or hot chocolate orders and everything is fine. But unfortunately, you can't assume that whatever you decided when you first started building your application is going to be the same forevermore. Ultimately, you're probably going to want to evolve your events. So for example, in the coffee shop demo, we might want to say, well, actually, if you're ordering hot chocolate, you can have an option to add marshmallows. So of course, the next time I place an order for hot chocolate, I will ask for marshmallows, and we'll get through to the barista with this true entry. But if the barista hasn't been updated and told we've got this new option for marshmallows, then they don't know what to do with this information. And if the barista has been written well, maybe this just means they ignore the unknown field and everything is fine, but the likelihood is that the barista wouldn't have been written with that in mind, so I might not even get my hot chocolate at all with marshmallows or not. And it's actually worse than this, because the coffee shop has so many different options that they could use to start this data in. You can write your own serializers for Kafka, so they could use JSON or XML, and all of these formats are options that then the barista would have to deal with if the coffee shop decides to change what they send in. So when you're running applications with Kafka, you need to think about what shape are your events going to have, how is that going to evolve over time, and how do you make sure that your producers and your consumers are always talking the same language? So the first way we can do this is by starting to add a little bit of structure to our messages. So let's look at using JSON. JSON gives us great structure. We have our order ID, our product, our customer, and if I add an extra field, then most languages that have JSON integration will be able to ignore unknown fields. So the likelihood I'm going to break my barista is kind of reduced here. But although JSON gives us great structure, it lacks additional metadata and validation. So there's nothing to stop the coffee shop saying, actually, we've changed our mind, we're not going to use a Boolean for marshmallows, we're going to put yes or no as a string. And in this case, the barista would still struggle to understand this message. So this is where schemas come in. A schema is like a blueprint for your event. It's a way to document the shape of your event and what different fields should be part of that event. You can actually think of it as being very similar to the Open API documentation that a lot of us are already used to using. So if we have a schema, this means the producers and consumers can use that to understand these events. But where do we store the schema? So we could store the schema individually with the producer and the consumer, but this doesn't solve the problem of what happens if something changes. If the producer evolves their schema, there's no way for the consumer to know that something has changed. So what's the simplest way that we can create a schema and make sure that our consumers can always read a message? Well, we could include the schema in the message. So in Kafka, we could write our messages in JSON, we can put the schema in that JSON object, serialize it, send it off to Kafka, and then when the consumer gets it the other side, they can deserialize it as JSON and then have a look at the schema to understand the contents of that JSON object. This works okay, I mean, it does the job. However, it does mean that you then have to have a schema in every single message that you want to send. And the bigger the messages you're sending, then the more that affects your throughput. And you're having a lot of repetition because ideally you don't want to be changing your schema every single day, but you do just want that option to change it if you do need to. So that's where a schema registry comes in. A schema registry provides a central store for all of your schemas for your events. And as long as your producers and consumers can access a schema registry, then you're all good. So schema registries can be used with all sorts of different messaging systems. But for Kafka specifically, there are a few things that you need to be aware of if you're going to start using schema registries with Kafka. And we fundamentally have to answer two questions. One is, what format am I going to choose for my schemas? And the second one is, how do my consumers know which specific ID they should be getting out of the schema registry? So first, let's look at schema formats. These are the three most popular schema formats that I've seen being used in the Kafka community: JSON schema, Google Protocol Buffer, and Apache Avro. So JSON schema is a vocabulary that allows you to annotate and validate JSON documents. So you can see an example here on the right. We've got a type of object, we've got different properties, and we can say that a product is of type string, customer is of type string. So this already gives us quite a good structure to say, this is what my event should look like. It does allow you to describe your existing data formats, and it provides clear human and machine readable documentation. So this can be a good fit if you know you want to stick with sort of JSON-based schemas. Another option is to use protobuf. So this is a mechanism for serializing structured data. It's created by Google, it's language neutral, and supports generated code in Java, Python, Objective-C, and C++. You provide a .proto file where you define your schema, and then you can use Java classes, for example, to create objects that are based on that schema. So for this one, you do have to learn the kind of structure and how you write a .proto file, but you can have some really nice integration with your specific code. So you can see the Java ones here, it's very easy to use. The one that I've seen used the most is Apache Avro. So Apache Avro is a data serialization system that provides very rich data structures, but it also provides a compact, fast binary data format. So for Apache Avro, you can serialize the data into binary or into JSON. So the binary option is obviously a great fit for Kafka, but you can use JSON as well if you want to. And it provides simple integration with dynamic languages. So this means if you don't want to do code generation, you actually don't have to. So if you want to use Avro, you have to define a file that looks like this. You need 3 entries at least. So you need a type, which in this case is record, a name, and then fields. And you'll notice that schemas for Avro are actually written in JSON. So it's very easy for someone to pick up and start writing an Avro schema if they've never done it before. They just have to make sure it's in this structure. Then you can provide the different properties. So for example, here I have a product and it's got type string, but Avro also provides additional metadata you can provide. So for example, I've got a logical type here, which is a unique ID. They also provide logical types around dates and times. So those are the ones that I see people using quite a lot because it's really useful to be able to define a specific entry as a date or a time rather than just using a string, say. So once you've defined your schema, you can then utilize it from Java. So this is an example, and this is where I was saying that with Avro, the advantage over protobuf is you can use a generic class. So here we have a generic data class, and this allows you to construct a new object based on the schema. So you can see we've provided the product, the customer, and then marshmallows as tree. So the good thing about Apache Avro is if you want to, you can move forwards and start actually just generating classes, and you could create a specific order class the same way that I showed for protobuf. But for Apache Avro, to start off with, you can just do it like this, and it makes it a lot simpler in terms of the dependencies that you need to write your first application. So we've looked at some different data formats that are available. So now how do you decide which schema to choose? And this is where you have to take into account the specific schema registry that you have chosen to use. So when you're identifying a schema, first we need to find out how do we uniquely identify this schema at this specific version. And that does depend on how the schema registry references its schemas. So there are some schema registries that, even if it's the same named schema, the different versions have their own unique ID. So here you can see an example where I've got ID1, ID2, and those could be the same schema, but just different versions of it. Or you can have a schema registry where for a specific named schema, so for my order schema, it has an ID that refers to that name of order, but then within that, it has different versions. If your schema registry works like this, then it means you need a combination of the ID and the version to uniquely identify that specific schema. So once we've identified how we're going to pick out the schema, how do we make sure that our consumers for Kafka actually get hold of this information? And this is where we kind of need to talk a little bit about how Kafka stores its information. So In Kafka, an individual event is called a record. This is because you can send events or messages depending on what you're doing, but a record is basically a key and a value pair. Now, keys are optional in Kafka, so you don't have to provide a key. So normally the bulk of your message goes in the value, and then the key provides some additional information that Kafka can use for sort of routing and things. So we have this key and this value. There are two different ways in Kafka that you can send the schema ID across. And the first way is using something called a magic byte. So imagine this is the bytes of a value of a record that has been put into Kafka. This value has been updated so that it includes magic bytes. So what this means is that the producer has sent this through Kafka, and when it's received by the consumer, to deserialize this message, will split it into 3 different parts. So the first part is a magic byte. This is basically something to indicate to the consumer, by the way, this value has a schema ID in it. It's not just a straight value as an event. The second section provides the integer schema ID. So this is the way to uniquely identify the schema that is being used for the message. And then finally, we have the actual serialized data. So a consumer can make use of these 3 pieces to understand, I've got a magic byte, therefore my schema ID will be next, look at the schema ID, and then use that schema to deserialize the rest of the data. And because we have both a key and a value in Kafka, if you want to, you can actually use schemas for both the keys and the values. It's fairly common for people to leave the keys as just strings, but if you want to, this is definitely an option that's available to you. So you could have all of your keys and values coming through with these magic bytes on the beginning. So the great thing about this approach is that all of the information about the schema ID is included in your message. We haven't got the problem that we had with including the full schema that we did before. It's a very short set of bytes that you're having to pass each time. So this makes it great in terms of the consumer receiving the message and being able to easily deserialize. The disadvantage of this approach is you have actually polluted the contents of your message. So in Kafka, you can send through null values, and that does specific things depending on your configuration. And this becomes a little more difficult when you're always adding a schema ID and a magic byte on the beginning. So this is a great option, but you might want to consider looking at record headers instead. So record headers. In Kafka, I said we have a specific record is made up of a key and a value. Well, in 0.11.0, they also added a record header. This is a sort of concept that has actually been included in a lot of different messaging systems over the years, and it's this idea of having additional metadata that you can pass through with your message. So to add a header in a Kafka record, it's actually really straightforward. You just, when you're creating your producer record, you can do .headers, .add, and then there it is. So what this means is that you can, instead of passing the schema ID as part of the message and doing all the magic byte part, you can just add it in the headers. This is really handy because it means if you need to pass more than one identifier, so in this case we've got an ID and a version, you can just pass them as separate headers. It also means you're not polluting your actual contents of your message. You're just sending through the message nice and clean and then adding the headers with the schema information. So we have these 2 different approaches. You can either include the schema ID with a magic byte in the key or the value, depending on which entry is using a schema, or you can add all of the information for both the key and the value schemas in the headers. But the important thing to note is when you're producing and then consuming, the consumer needs to know which one to look at. So if you produce and put it in as a magic byte and the consumer is looking for a record header, then you're going to have a problem. So you need to think about when you're sending your messages, how do you make sure that they're lined up? And this is where we come back to your schema registry that you've chosen and specific classes that you use with it. So I'm going to talk a little bit about SERDES and converters and basically how you can set up your Kafka applications to actually use the schema registry that you have chosen. So in Kafka, we have 3 different types of applications. We have producers, consumers, they're the sort of standard ones you start with. We have connect, which allows you to pull from external systems and go into Kafka or go out the other way. And we have streams. All of these different types of applications have different configuration options for you to tell it how to serialize and deserialize the data. So if you're using a producer consumer, you provide for the producer a key serializer and a value serializer. And for the consumer, it's key deserializer and value deserializer. So for whatever schema registry you have chosen and whatever format you want to use, you need to make sure that you use the right class so that it will serialize the data using magic bytes or the headers, whichever, and then the consumer can deserialize. For connect, you provide what's called a converter. So it's the same way you have a key option and a value option, and you do key.converter and value.converter. And there are 3 that are provided by default: the JSON converter, string converter, and byte array converter. But these are all working on the assumption that you're not using schemas. So for your specific schema registry, you'll need to find the right converter that will convert and serialize the messages and then deserialize them based on your schema. And then finally, we have Kafka streams. So Kafka streams, again, use a different setting, which is the key SERDE and value SERDE. So SERDE being short for serializer, deserializer. Again, there are some default SERDEs that you can use. So if you're not using schemas, then you can use the string SERDEs or integer. But for your specific schema registry, you'll have to go and find the SERDEs that you want. So the thing to bear in mind is if you've got a system that's set up like this, where you've got something coming into Kafka Connect, then you're processing it in Kafka Streams, and then you're consuming it, you have to make sure that your converter, your SERDEs, and your deserializer all know about your schema registry, are all using the same mechanism for storing that schema ID, whether it's headers or magic bytes, and are all configured with the same format. Otherwise, you might find some strange stuff going on as your messages flow through the system. So hopefully that's given you kind of a good intro for how to start using schema registries. The last thing I wanted to do is just promote Apocuria Registry. So this is an open source schema registry that provides multiple different format options, including Avro, Google Protocol buffers, and JSON schema, and it provides multiple storage options as well. So you can store the schemas in Kafka itself using streams or in things like Postgres. The great thing about Apocuria Registry is it actually provides IBM and Confluent compatibility APIs. So what that means is if you use a converter or a serializer or a SERDES that's provided by Confluent or IBM, actually you can use them to talk to your Apocuria Registry. So you don't have to just stick with the ones that Apocuria Registry provide. They do provide ones, however, so if you want to use the Apocuria Registry ones specifically, you can go and find those classes as part of the project. So for example, these are the ones for Avro. I'd highly recommend having a look at Apocuria Registry. It's a great project, and they have a Kubernetes operator as well if you want to run it in Kubernetes. So with that, I will summarize. So you should definitely look at using schemas to get structure into your events. If you don't use schemas to help evolve your events over time, then you're likely adding a lot more decoupling than you think you are by moving to this event-driven architecture. Definitely use the schema registry to provide centralized store. There are quite a few different examples out there, but if you want to start with a basic open source one, then check out Apocuria Registry. And finally, you need to think about and choose your favorite format and identification mechanism, but make sure you're configuring it to do the same thing across the board. A good thing about Apocuria Registry is it does provide both the magic bytes and the headers option, so you can choose whichever one suits you, but you need to make sure they all match up. I mentioned that I work on event streams, so this is a fully supported Apache Kafka offering, and if you're interested in learning more, then feel free to go to that link or ping me on Twitter. And with that, I just wanted to say thank you very much for having me, and I've provided a whole host of links. So I'll share the slides as well, but if you want to get an intro to schemas, we have a whole section on our docs for event streams that you can check out. And Apicurio Registry also have a lot of docs about specifically running their stuff. And then I also supplied some links for getting started with Kafka. So there's a quick start guide, Strimzy, which is a Kubernetes operator for Kafka, and a starter app if you want to have a go at just running something and seeing a nice UI for producing and consuming. So that is it from me. Thank you very much for having me.
Thank you so much, Kate. I'm not a Kafka developer. I don't work with Kafka. I know what it is. I think I do. I think I do. And because of that, yeah, in my early days of hardcore Java development, I was like all JMS. Like everything would go to JMS, right? And it's interesting because the question I have here from someone watching the conference is exactly about message brokers. So seems that for message brokers use case, Kafka is not exactly the best or good fit, or it is good for streaming, such as clickstream events, etc. Could Kate comment on message broker use case? Could you?
I can. So I've actually recently put out an article talking about specifically this and the difference between message queuing, event streaming, and message queuing systems were built for a very specific purpose in terms of the request response style messaging, whereas Kafka was originally built up as a distributed event log, and there's very much like publish subscribe. Kafka and things like IBM MQ, which is the one I'm most familiar with as a message broker, they work really well in slightly different use cases, but they also are both very configurable and can kind of do things in the middle. So what we've actually found is a lot of people are starting to look at Kafka primarily for this sort of event history and the scalable consumption. The fact that you can replay messages and reread them and have multiple different consumers all connected is a really, really good feature of Kafka. And a lot of message brokers that provide publish subscribe, when you add a new subscriber, they're actually creating a copy of the whole queue. Whereas in Kafka, that's not what's happening. So you can scale out to a lot more consumers with Kafka without having as much overhead as you would with a message queue. So often what we find is people are starting to actually use them together. So they're using things like IBM MQ for maybe that very targeted request response, wanting very reliable delivery, and then actually flowing a lot of those messages into Kafka and allowing a whole host of consumers to read those messages and then do other things based off of that. So you can actually use them really well together. And that's why we provide connectors for IBM MQ for you to flow data between the two.
Excellent. So I do imagine that there are connectors for all sort of message brokers, though, not just IBM MQ, right?
Yeah. Okay. So the MQ ones are the ones that I wrote. But,
of course.
So, but yeah, there's plenty out there. If you go and have a look online, there are loads of different connectors. And the really nice thing about Kafka is they built it so it's really extensible. So any Kafka Connect connector, you can plug into any Kafka, whether that's the open source Kafka, Strimzy, or event streams. You can just plug any connector in and off you go. So that's one of the reasons I love Kafka.